Okay, so I wanted to make this video just in case you didn't get to finish the protein folding activity, or if you just needed a review of what was going on. So we start out with a DNA strand, and DNA is the genetic material that codes for pretty much everything in your body. We're trying to make proteins, which pretty much carry out the functions of everything in your body. So first we're going to start with the genetic code. So what we have here is a DNA sequence, see kind of running off the page. But you have a DNA sequence that's written in blue, and we know it's DNA because it has thymine in it, which is represented by the T's. So DNA base pairing rule is that A always pairs with T and C always pairs with G. But we are not turning it into DNA, we are transcribing it into RNA. So when we transcribe it into RNA, we are going to write this in this kind of magenta color, and instead of pairing A's and T's and C's and G's, I will pair A's and U's and C's and G's. So T still pairs with A, because A is one of the letters of the RNA alphabet. C will pair with G, and again T and A. Now A will pair with U, C will pair with G, G will pair with C. T will pair with A, T will pair with A will pair with U, C will pair with G, T will pair with A, G will pair with C, A will pair with U, G will pair with C, A will pair with U, A, G, U. Okay, so hopefully all of that makes sense. We have now transcribed into RNA, and this is going to be the code that tells us what amino acids we are going to have in our primary structure of our protein. So all of these 3 letters of RNA are going to code for a specific amino acid. And we don't have to memorize those. We have this nifty little chart right here. And so we use this chart. Looking at it first, we have, see if I can get this to work. All right, there we go, the best I can do. So your amino acid, you have AGA. So I'm going to start A, and then I'm going to find G, A. So that is ARG. I meant to use this color pink, so I'm just going to write on top of it, ARG. So that goes with that. So UGC, we're going to go UGC. That's coding for CYS. AAU, we go AAU, that's going to code for ASN. GAC is going to code for GAC, ASP. And these are just the abbreviations for the fancy names of the amino acid. This is like arginine, cysteine, asparagine, etc. UGU is cysteine as well. And then AGU, we have AGU is going to be serine, S-E-R. So right here, we have translated, our RNA sequence, and we have figured out what amino acid sequence we're going to be looking at. So you have 21 different amino acids, and it's similar to how there are 26 letters in the alphabet. So all the combinations of the letters and the order of those letters are going to give us all the different words in the world. And similarly, all the different amino acids and the combinations of the amino acids, the order of the amino acids, give us all of the different proteins that carry out all of the functions in your body. So the pipe cleaner here is going to represent the amino acid backbone. An amino acid is made of 2 specific groups in the backbone. So looking at this is a model of an amino acid. Here you have, these are both carbon, the black is carbon. This carbon is double bonded to an oxygen and single bonded to a hydroxyl group. And so this is going to be your carboxyl side, and these are also called carboxylic acids because they can donate this hydrogen. And then over here you have your nitrogen group attached to 2 hydrogens, which this is your amino group. So that's where we get the term amino acid, because all amino acids have this amine group and this carboxylic acid group. Now they also have this little pink thing that's sticking up, and this represents the R group. Now the R group is the same thing as like a variable in algebra. It's like an X. It can kind of be anything. And there are 21 different R groups that we know about that make up the 21 different amino acids that we're talking about. So this is the basic structure of an amino acid, and they're all going to link up to form a long chain called a polypeptide. And the polypeptide folding is going to determine the protein shape. So here, the pipe cleaner is going to represent my amino acid backbone. So looking at the chart that you guys had, I'm going to find the bead colors that would be represented by the amino acids I have determined. So ARG would be a purple bead, so I'm going to string a purple bead on here. CYS, cysteine, is going to be a green bead, so I'm going to put a green bead on next. ASN is going to be a blue bead. The next one, ASP, is going to be pink. CYS we already determined was green, so I'll put on another green one. And SER is going to be blue. So there's obviously a lot more amino acids that make up a polypeptide chain, but this is just representative that you have your amino acid backbone that has the amino and the carboxyl group, and the different color beads just represent that there's different R groups that are attached to each of those amino acids that give them certain characteristics. So right here, just this string of beads that we have that correlate to the amino acids, this is our primary structure. So right here we have primary structure, and it's just a sequence of amino acids. All right, primary structure, nothing exciting, just a string of beads. Now, secondary structure, what happens is the amino acid, the carboxyl and amino group start to bond with each other in hydrogen bonds. So the pipe cleaner is making up the carboxyl and amino group, and so you're just going to have it start to bond with the other carboxyl and amino groups through hydrogen bonding. Oops, just lost the bead. Okay, so you're going to get these things like coils, and this would be considered our alpha helix, where you get coils. Or sometimes it zigzags, and you get something we call a beta pleated sheet. So if the hydrogen bonding occurs and makes it look like this flat zigzag, we call it a beta pleated sheet, and if it coils to give you kind of this three-dimensional coil, that's called an alpha helix. And both of these can occur in secondary structure. It's just depending on how the hydrogen bonding occurs between the amino and carboxyl group. So I have an alpha helix here, I have a beta sheet here, and I'm going to finish off in an alpha helix because it's easier. So here we have the bonding, the hydrogen bonding between the amino group of the backbone and the carboxyl group of the backbone. So I have a model here that shows a more official looking beta sheet. So here you have your, all of these represent the peptide backbone. So you have the carboxyl group in red, the amino group in blue, and you can see the white is where the hydrogen bonds is occurring. So there are no R groups attached to this. This is just kind of a naked backbone showing how the beta sheet will conform, and you can see it's kind of this zigzag thing where there's just bonding only occurring between the OH group of one and the NH2 group of another. So hydrogen bonding can occur between oxygen and hydrogen, and it can also occur between hydrogen and nitrogen, and so you have this hydrogen bonding that's occurring. This would be an example of an alpha helix. You can see it's more of a spiral, and again the hydrogen bonds are now vertical like this, and that's holding it in that coiled position that we looked at. So these again are just kind of showing you how it's only the backbone bonding in secondary structure. And if we add on the R groups, you can see it starts to get a little fuzzier, where the backbone is still what's holding it together with the hydrogen bonds, but now these R groups projecting, they're going to start interacting with each other as we get into tertiary structure. So right here, we just have our secondary structure where only the pipe cleaner is kind of bending on itself, bonding with itself, and the beads haven't really started to come into play yet. And the same thing here. You have the interactions of the backbone hydrogen bonding, but the R groups haven't really come into play yet. So now what happens as we have these characteristics of these functional groups? So it's going to start taking on this three-dimensional shape. So I'm going to kind of put the edges together like this. And now I'm going to see kind of what starts to line up. But to, first I need to figure out what the characteristics of these R groups are. So the R groups can be classified based on their kind of their characteristics. And so in your book, it tells you on page 77, this is just a little snapshot of it, it tells you these are the polar side chains, these are the electrically charged side chains, you have your acidic, which are negatively charged, your basic, which are positively charged, and then you also have your nonpolar side chains. So the beads, I didn't choose any beads that were going to be nonpolar because it's kind of hard to represent what they do. But if we look at the chart, I can't show the chart and this at the same time, but looking at the chart, I see that ARG is going to be positively charged. CYS is going to have a sulfur in it, so that's going to form a bridge. Cysteine is like the special one that likes to form bridges with other cysteines. ASN is going to be polar. And anything that's polar is probably going to have the ability to hydrogen bond. ASP is going to be a negatively charged. Cysteine, again, is going to have that sulfur, which wants to form a bridge with another sulfur. And these are probably the most stable covalent bond that's going to occur to hold your molecule together. And then serine is also going to be polar. Now, if you do have any nonpolar groups, again, it's hard to represent with the beads because they don't really like to form bonds. But what they want to do is they want to get as far inside of the molecule as possible. So this is a fancy version of a tertiary structure, and you can see all of these that are inside must be nonpolar because they're trying to get as far away from the water as possible. So we think of these proteins typically in the body in an aqueous environment, meaning they're in a watery environment. And when you put them in there, all the polar side chains are going to want to stick out and have access to the water, and all the hydrophobic or nonpolar ones are going to try and tuck themselves far away as possible into the inside. So this is a fancy version of a tertiary structure. You can see right here you have your beta pleated sheet, and that looks like there's some alpha helices down there. But now all the R groups have interacted to form this really complex 3D structure. And at this point, it can be considered a protein unless it needs to associate with other proteins to become effective. So here's my less beautiful version. But we're going to start seeing which of these chains might interact. So I know my arginine and my asparagine have charges, so we're probably going to have them attract. So one is pink and one is purple, and so these beads are probably going to try and bond together. So let's see if I can get my paper clip to bond these. So the idea here, you have formed a bond, and that's just like an ionic type bond between a positive and a negative. Between my cysteines, I'm going to have some kind of bond form. They're going to form one of those stable bridges, and so I'm going to put a bond between those. All right, so it's starting to take on this 3D conformation. Again, these paper clips are representing bonds, but they're really giving it a definite shape. And if you don't have bonds, it's just going to turn into a big circle. So you need to have bonds holding it together so that you have a really specific shape, because we know shape equals function. And then we also have, I might try and twist it around so that it works better. So now we have these blue ones. Both of these are polar, and polar can typically have hydroxyl groups or something that can hydrogen bond with each other. So I'm going to put this between them to represent a hydrogen bond that's creating. So obviously this isn't perfect. They make computer models to determine this stuff. But we have tertiary structure where it's actually starting to have interactions between the R groups. So you have primary structure, really nothing going on except a string of amino acids. Secondary structure, we talked about how it forms these sheets and the hydrogen bonds hold them together. But tertiary structure is where these R groups start to come into play, represented by the beads, and the R groups start to bond together. And then you're going to get this really complex looking thing like this, which is a three-dimensional protein that has a really specific conformation, and all the bonds held between the R group are what gives it its specific shape. Now our final structure is quaternary structure, and that has to do with multiple polypeptide chains coming together to be a functional protein. So if this lovely little hairball could go off on its own and do functions in the body, it could be considered a protein now. So quaternary is kind of considered like an optional one. It's the only one that's optional out of the different structures. And it only happens if it needs other proteins to function. So if you have an association of multiple polypeptide chains working together, then you have, this is just some buddies that they left in the room that I borrowed, and it's going to, their little hairball and my little hairball, if they form an association, you get more of like a complex structure even still. This creates a special shape that will then become a functional protein. And then again, that protein can go off in the body and do whatever it needs to do. So using the more fancy models, you can see if like this one had to stick with this one, then they would create this highly complex dimensional structure that would then go off into the world and do whatever it needed to do. And this would be an example of quaternary structure. Now, proteins can lose their shape, and we call that denaturing. So if for some reason it was exposed to heat or pH or something, it's going to start deteriorating these bonds. If I can get this paper clip off, we'll just pretend like that came apart. And then as that happens, then it's starting to lose that complex shape. It disrupts the hydrogen bonds. It disrupts the cysteine bonds. It disrupts the secondary structure with the hydrogen bonds in the backbone. And basically it's just going to flatten out and turn into a primary structure again. So it just turns into something that is not functioning anymore because it doesn't have its specific shape or conformation. So a lot of things are messed up when the proteins are denatured because they can no longer work. And so like when you cook eggs, the reason it goes from like egg whites into the hard eggs that we eat is because you denature the proteins, which turns them into a solid, totally changing the conformation. So change the shape, change the function. So denaturing proteins just kind of undoes all of your hard work when you folded them up together. If you denature it, it's just going to kind of turn back into a string of amino acids where if the conditions are right, it might be able to fold again. If not, it's just completely denatured and rendered useless. So that is protein folding and structure, and hopefully that helped and made sense, and I will see y'all later.